So get your books out. Yay! All right. Part 4, yeah. Right after 3 and before 5. Yeah.
I thought we got to part 7.
Yeah, but we didn't do 4.
Yeah.
Okay, so hydrated salts are just a compound, but the word hydrated, you might think of water, and you're right. So a hydrated salt basically has what we call waters of hydration associated with an ionic compound. I sound like such a snob and say ionic, but we said that actually you know you have an ionic compound if you have a metal in it. Okay, if your formula has all nonmetals and hydrogen is considered a nonmetal, then your type of compound is a molecular compound. So an ionic compound with waters of hydration. Okay, so you're going to see it in the formula of a hydrate. So for instance, this is a formula of a hydrate. The ionic compound is just barium chloride. The dot means, after the dot means it's going to show you waters of hydration. So for every, if you can kind of picture this, you're going to see a picture of an example, but for every BaCl2 formula unit, you're going to have 2 waters of hydration surrounding them. It's just what they do. So I would call this BaCl2 dot 2H2O. We're going to talk about nomenclature actually in, I think maybe it's unit 4, how you name compounds. But I'm going to tell you that very rarely do we do the prefix DI indicating T2, excuse me. But here, with regard to waters of hydration, we do use those prefixes. So that's barium chloride dihydrate. This is copper 2 sulfate pentahydrate, 5 waters of hydration. And you can see kind of in these peach colored things, we're going to be using this to our advantage. Do you see, for instance, we'll pick on copper 2 sulfate pentahydrate. Do you see for every 1 mole of the salt, we have 5 moles of water. And that 5 moles of water is coming right from here, okay? Iron 3 nitrate, nano meaning 9, hydrate. So here's your salt. For every unit of that, for every 1 unit of the ionic compound, or for every 1 formula unit, we have 9 waters of hydration. Cool. So picking on magnesium sulfate heptahydrate, you have to kind of look hard, I think. Magnesium. So magnesium sulfate itself is 1 magnesium cation, that's the metal. And then here's the sulfate, SO4, so MgSO4. Then if you kind of look around it, you're going to find 7 waters of hydration. So that's how that looks like in its solid state. I'll warn you though, and actually this is a player in one of the problems we're going to do. If you take that solid magnesium sulfate heptahydrate, and if you go ahead and dissolve it in water, guess what? Those waters of hydration do. They just mix up with the waters that you dissolved it in. So basically those waters of hydration flake off. Ionic compounds like this dissolved in water will break off into its magnesium and its sulfate too. It'll be aqueous. So you maybe have seen these but didn't know it. This cobalt 2 chloride makes a good moisture indicator. It turns colors. We're going to be doing some problems where you can take the hydrated salt, that's the pink one, dry it, and get the anhydrous salt. That's the blue one. Yeah. Now, you like the colors. Now, here's one thing about it. Do you know, and I don't know if this make a good desiccant, but those desiccants, when you buy like pills or something or a purse, they have like these little packets they do not eat. Mm-hmm. It's a little desiccant.
Silica gel?
Yeah, silica gel. Something that takes in waters of, so that would be a good desiccant. Okay, here's the dry. We call the dry anhydrous, and this one has 6 waters of hydration for every cobalt 2 chloride formula unit. Okay, let's work a couple problems. And actually, this part 4 was one that Alta doesn't have. So I'm going to give you a paper here that's going to be due on, I think I said Monday. So no Alta homework for this one. So we have an example here where we have nickel 2 chloride hexahydrate. And the question is, how much water do you have if you have 3.50 grams of that salt? Okay, so I'm going to show you a way to work this, and there's probably more than one way to work this, but I'm going to show you the way I do. Which reminds me, I'm just looking at some of the Alta homework that y'all are turning in, and they do kind of a cool thing with the limited reactant. So if you do their process of identifying the limited reactant, that's fine too. They basically take, they come up with they have moles of the reactants, and they divide the half moles by the stoichiometric coefficient in all cases, and then they find out which one's the smallest, and that's the one with the reactant. So anyway, so if you picture what this is, we basically have this compound, it's in its solid state, and we want to knock out of that weight of 3.50 grams, some of that's water. So a good way to do this is to kind of knock out the molar masses of the pieces and the whole. So we're going to use a periodic table. We're going to look up nickel, so we're going to take 1 times 58.69, nickel 2 chloride, plus 2 times that 35.45, that's the chlorine. And we get a molar mass of the anhydrous salt of 129.59 grams per mole. To work this sort of problem, we're going to need to know what's the molar mass of just regular old water. And this is one that we do a lot of molar masses and a lot of using water. So we do a lot of molar masses of water. So of course that would be 2 times 1.008 for hydrogen, plus 1 times 16.00 for oxygen. We're only allowed 2 decimals, so that rounds to 18.02 grams per mole. For the hydrogen, for the water. And then to work this, and you'll see where it enters in, I want to knock out what the molar mass of everything is. Well, basically, I'm going to take this number, which was the anhydrous salt, plus 6 times this number. Does that make sense? So I'm not going to reinvent the wheel down here. To knock out the molar mass of the hydrated salt, I'm going to go back to the first number, which was 129.59. I have 6 waters of hydration, so that'd be plus 6 times 18.02. So the molar mass of my hydrated salt is 237.69 grams per mole. Okay. Now notice when I work this for myself, an answer key or whatever, I like to label things. So notice I didn't have to be explicit for instance, the first molar mass. I didn't have to say 129.59 grams of NiCl2 per mole of NiCl2 because I labeled it. So, all right.
How are you being 6 times? I didn't get that.
Okay. Well, assuming these numbers are correct. So if we go with, in chemistry, what we do a lot is making our bases. And I'm going to make the basis 1 mole of the hydrated salt. Okay. So actually, as I'm working this problem, I'll look at it afterwards. So if I look at it afterwards, if I look at 1 mole basis, that means I have 137.69 grams of the hydrated salt. Why? Because its molar mass is 237.69 grams per mole. So, and we want to knock out in that given mass of hydrated salt, how much of it's water. Don't lose that. So if we simply take, so we could come up with, in general, and I think this is actually one of your first homework problem, if we want to know what the mass percent of water is in this hydrated salt, we do what we know about coming up with mass percents. We take the mass of the component of interest, which is water, so 6 times 18.02 grams of H2O, and we divide by the mass of the total mixture, which in this case is the hydrated salt. 2.37.69 grams of the NiCl2.6H2O. So that's giving us weight percent of water. Okay, so you're looking at 45.49% H2O. Let's see if I can find my. So what that means is I have 40, and you're going to see this on the next slide. You're going to have to unpack weight percent. So what that means is 45.49 grams of H2O in 100 grams of the hydrated salt, which is your NiCl2.6H2O. Okay, so I'm going to use that to my advantage to knock out this problem. So the last thing we're going to do then is go back to the original problem. It says the mass of the hydrated salt was at 3.50 grams of NiCl2.6H2O. Now I'm going to ask this in the form of a question. On a previous slide, I put a ratio. So how can we go ahead and get to grams of H2O? Do we use that percent you saw on the previous slide as it is, that ratio, or do we flip it? Flip it. How many people think we flip it? How many people think we leave it the same? We just leave it the same because then the units of the NiCl2.6H2O will cancel. Yep. And that's it. And if you look at your units, you have what the question is asked. So you have units of grams of H2O. So we take it 45.49 grams of H2O over 100 grams of NiCl2.6H2O. So how many sig figs? Three sig figs. So you're looking at, based just upon the formula and the original mass of the hydrated salt, you're looking at 1.59 grams of H2O. We're going to do not a follow-up problem. We're going to do another problem here. Just keep in mind, kind of envision what we're doing. We could dry that 3.50 grams of hydrated salt, and this would be the amount of water that would be driven off. All right. So for this one, I kind of think of it as I like to kind of picture these things, as you know. So if you read it a few times, we're dealing with copper 2 sulfate, but we don't know how many waters of hydration there are. So here's my pile of CuSO4.X. We don't know how many waters of hydration there are. I'm going to heat it, and I'm going to end up with a smaller pile of just the anhydrous salt, CuSO4, and I'm going to end up with H2O is also going to be driven off. Here's my little H2O. So it tells me that I start with 1.023 grams of the hydrated salt, and the problem tells me that I end up with 0.654 grams of the salt without the waters, the anhydrous salt. Can we get to the mass of the H2O? Yep. I'm just going to say by difference. I have it on the slide coming up. Yep. So I can get to that by difference. So I'm just going to kind of tell you, and then I'm going to show you. So can you see where you get this? You got this mass. You know how you can get this mass by taking this and subtracting this. So once you have these masses, do you see how I can get to moles? When in doubt, use the molar mass. And once I can cut with relative moles, I'm almost done. So that's kind of a big picture of what you're going to see down here. So here we go. We need to find out how many moles of water we have per moles of the salt, CuSO4. So we're going to need some molar masses. The molar mass of the anhydrous salt is 1 times 63.55 for this copper, plus 1 times 32.07 for the sulfur. We have 4 oxygens, so plus 4 times 16.00 for the oxygen. So that's the molar mass. So we end up with 159.62 grams per mole. That's the molar mass I can use with this 0.654 to get to go from grams to moles of copper 2 sulfate. We're also going to need the molar mass water. So we have 2 hydrogen, so 2 times 1.008 plus 1 times 16.00 molar mass of water is 18.02 grams per mole. And we can use that molar mass to get to moles. So then here we go. Oh, before I start, I'm going to go ahead and knock out, you guys told me I could get this by difference. There it is by difference. Don't forget, when we're subtracting like this, we round according to decimals. So if we take the mass of the hydrated salt, 1.023 grams, and from that subtract the mass of the salt without the waters of hydration, you get subtract 0.654 grams. You're looking at 0.369 grams. All right. So moles of water, we're just going to take that 0.369 grams. You guys have been doing a lot of these. What's the next term to get from grams to moles? The molar mass, yeah. How do we use the molar mass? 1 mole H2O over 18.02 grams. Grams will cancel out with units of moles. How many sig figs? 30. So to give it 3 sig figs, this is one of those deals where this 0 right here after the decimal, it's just showing what I call magnitude. The 2 is significant. The 0 between the 2 and the 5 is significant, and of course the 5 is significant. So for the next one, we're going to use this mass, 0.654 grams. See, this is why I like writing a picture, because I'm like, oh, I can see that. We're going to use the molar mass of the anhydrous salt, 1 mole over 159.62 grams. Again, round to 3 sig figs, and you're looking at, wow, 0.00410 moles of copper 2 sulfate. And you know, I've been talking in here about labels and kind of laying things out. You label for a number of reasons. One is so you can follow what you're doing. But can you see where if I label my step, in blue is the labels of my step, then I don't have to worry about what I call explicitly labeling these masses and molar masses. All right, so the last thing, since we have the moles of the anhydrous salt and the moles of the water, all we got to do is knock out the ratio. So that is that little slash there, that means divide by a ratio. So from the previous slide, if you just grab that 0.0205 moles of H2O divided by 0.00410 moles of CuSO4, we're going to round to what, 3 sig figs? In this sort of problem, let's see, I think this is right. You're hoping for a whole number, okay? And we did get a whole number. So, yeah, you have to think. I don't think waters of hydration go for, I think that's right. So the X here is 5. So we can go ahead and write the formula now. It'd be CuSO4.5 H2O. Voila! I see some of my subscripts didn't make it. So sorry about that. Let me know if you have any questions about these formulas. It kind of died in translation. So this will be due on yeah, on problem 2 and 3, my little subscripts didn't work.
Thank you.
Okie dokie. Non-Alta homework due Monday. And
Do you know the subscripts that are not in here?
so the subscripts for problem number 2 it should say, for problem number 2, it should say MgSO4, that 4 should be a subscript, bless you,
Yeah, thank you.
dot XH2O, that's kind of like a problem we just worked. For problem number 3, it should say Na subscript 2 SO subscript 4, excuse me. And the formula you see in that problem is Na2SO4 dot 10H2O. I'll probably print off another one and give it to you mañana. Remember tomorrow, there's a few people, if you make sure you get with your lab partner, but this is one of those where I've granted permission for people to start at 11, so if you want to, you can start at 11. Otherwise, it'll start at 12. And the people that do it early will have to kind of segregate you a little bit. So, there you go. Okay. On to part 9. So, here we go. Switching gears. So we need to talk about how do you describe how concentrated a solution is. I'm going to kind of remind you of what a solution is. We talked about a substance can either be a pure substance in which it's an element or compound, or it can be a mixture. And then we have 2 types of mixtures. We have homogeneous mixtures and heterogeneous mixtures. This is part 9. Okay. So actually, a solution is an example of a mixture, specifically a homogeneous mixture. So it's well mixed throughout. A cool thing about mixtures, whether they're homogeneous or heterogeneous, is you can separate them back out into their components. Okay? So we need to kind of focus on solutions and how do we describe how concentrated a solution is. Okay? So we tend to, I'm kind of a, yeah. So I'm a visual person, like I said, and we a lot of times think of it like this. So this is my beaker. Da, 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 da. So we think of, there's too many S's on this topic. We tend to think of a solute, but if you get these in your mind, it will help. We tend to think of a solute being added in smaller amount to a solvent. Okay? And if you take the solute plus the solvent, solvents in greater amount, guess what? You get a solution. Okay? So that's kind of what's going on when we talk about all of these S's. So when we talk about solution concentration, usually we're talking about the amount of solute present. Solution concentrations usually are, I'll just put AMT for amount of solutes per a given amount of total solution, usually. Amount of solute per amount of solution. Yep. And in Chem 2, we're going to talk about, switch gears and actually talk about another important way of talking about solution concentration in terms of solvents used. So these are generic terms. We're going to actually talk numbers here soon, but I'm sure you all heard of dilute and concentrated. So dilute simply means you don't have much solutes for a given amount of solution, and concentrated means you have a lot of solutes for a given amount of solution. So if you're just going to eyeball these, and actually we have colorimeters that can spit back a real number, but which one looks more concentrated? If I call this A or B? A looks more concentrated, just eyeballing it, exactly. So the caption says something like, actually in both of these graduated cylinders, we had the same amount of copper to nitrate, and we just added more water to B to dilute it up. Okay. Kind of intuitive. So I'm going to talk about the reason it says 2 new ways of describing solution concentration is the first one would be weight percent. I'm going to talk about 2 other ways. Okay, one, and let's not make it harder than it is. One is grams per liter, and I'm going to unpack this. Actually, it's G for grams, G of solute, like per liter L solution. I can't spell solution, but hopefully you got that. The other one we're going to talk about today, though, is moles per liter. Oftentimes called molarity. So this one is moles of solute per liter of solution. And we use a big M. Make sure it's a big M because there's something else for a small m. A capital M means molarity. Okay. So moles of solute per liter of solution. The caption down here in purple says, notice that these are all, since these are both relative to volume of solution, what do you know about, I think we talked about changing the temperature of a liquid. Like we take water and you cool it down, what happens to the volume, assuming it stays a liquid? You cool it down. The molecules become closer together, exactly. So it stays a liquid, the molecules slow down and they become more compact. So this is kind of chasing a moving target a little bit because your volume of solution will change with temperature. So this is okay, but you have to take that into consideration when you're talking about molarity or grams per liter. So let's work a problem. And even, you have to make a picture. You don't have to, but I think it's nice. Okay, so if you read this a few times, it says, and let's not make it more complicated than it needs to be, 32.3 grams of sucrose, I am going to add, and the formula for sucrose is given, I'm going to add it, and I'm going to, my total my total solution volume will be 225 milliliters of solution. So that's the volume of water plus the sucrose. So if I'm supposed to come up with, question mark, grams of sucrose per liter of solution, that's my target. Well, I'm almost there. I just basically got to take this number, divide it by this number, right? And that's all we're going to do. So we're going to need to clean it up a little bit. So our target was grams of sucrose per liter of solution. We're going to start with putting that 32.3 grams of, and you could spell out sucrose, or you could put C12H22O11 per 225 milliliters of solution. So how can I make the units of milliliters of solution cancel in the denominator and be left with units of liters in the denominator? How many milliliters in a liter? 1,000, yep. So I'm going to want units of 1,000 milliliters in the top and 1 liter in the bottom. Now my units of milliliters cancel. Milliliters of solution cancel, and I'm left exactly with what my target units wanted to be, which is grams of sucrose per liter of solution. Ta-da! How many sig figs? 3. Okay. So I would probably write it like this one that has a box around it, 144 G/L grams per liter, and then I would go ahead and say what my solute was, C12H22O11. Okay? We're going to do a follow-up question to the same solution. A really common thing to do in chemistry problems, because I guess it's a real-life application at times, is to take the same solution and to express it in different units of concentration. So, and when we do that, oftentimes we'll piggyback on what we already know, and that's what we're going to do here. So actually I'm going to write that the explicit way. We came up with the first part is a 144 grams of C12H22O11 per 1 liter of solution. Use that. So So a follow-up question to the same scenario is, what is the molarity of this solution? And what I like to do is kind of, you see this question mark down here? I like to write question mark, and I like write what my units are. So if I'm after molarity, I am after moles of C12H22O11 per 1 liter of solution. That's my goal. And I already have this one.
So you gotta multiply it by the molar mass.
I get to use the molar mass, exactly. And I'm going to use the molar mass to make sure that I get units of grams to cancel and be left with units of moles in the numerator. So actually it's going to be kind of divided. So here's the molar mass of C12H22O11. So we're going to take 12 times 12.01 plus 22 times 1.008. Then we can turn our attention to the oxygen, plus 11 times 16.00. It's kind of a small biomolecule, and we're looking at 342.30 grams per mole. And exactly what you said back there, I'm going to use that to my advantage. So if I use this as my first term, okay, my second term, I want grams to cancel and be left with moles in the numerator. So this is how I'm going to use that number. I'm going to put 1 mole C12H22O11 over 342.30 grams of C12H22O11. How many sig figs? 3. Just 3. And I probably would write it like you see this box right here. So 3 sig figs, you get 0.419. I put the capital M for molar, and then I put what the solute is. And the solute is that C12H22O11. 2 different ways to describe how concentrated this solution is. 1 in grams per liter and 1 in moles per liter. Okay. They're kind of like little brain teasers. Okay. So the caption reads something like this. KMnO4 is potassium permanganate, and it's kind of a purple solid, and we're going to use a volumetric flask, which I think I've talked about volumetric flasks before. They have this long neck, and it has 1 gradation up there that indicates to contain will be 1,000, probably 0.00 milliliters. So 1 liter, 1,000 milliliters. And we're going to dissolve it up with water. And it looks like this. So without getting your calculators out, what would be the concentration of that potassium permanganate solution in units of grams per liter?
If you put 1 liter.
Mm-hmm. Yep.
Oh, so then 4.75.
Yep. Very good. The concentration would be 4.75 grams per liter of the solute. Yep. Perfect. Okay. So this is again showing you the volumetric flask with 1 gradation here. A common, in addition to the 1,000 milliliters here, we have a 250 milliliter one. And the solute is potassium again, but it's chromate. So we using some weighing paper there. This is just to emphasize that if you are tasked with making a precise solution, what you want to do before you cap it off with liquid is you want to kind of have some sloshing around room in your volumetric flask. So hopefully it will all dissolve by that guy shaking his hand. And then after it's all dissolved, then you can go ahead and bring it up to the mark. Carefully. And if you used a stir bar in there to try to go ahead, it took forever because you didn't want to do this forever. You use a stir bar in there, which is just like a metal kind of thing about the size of my finger. They come in different sizes. Remember to take out your stir bar before you top up the volume, because otherwise that's not right. Your solutions are wrong. And if you, for that last dilution, don't forget to invert it a couple times. Actually, you guys are going to make your own solutions, not this week, but next Thursday. Don't forget to invert it a couple times. Otherwise, when you go to take your solution, it's going to be concentrated down here and not concentrated up here. Okay, all things to remember. So let's work another problem. So this is why I wanted to make sure we got the hydrated salt lecture under our belts. So what happens to those when we dissolve the nickel 2 chloride hexahydrate in water? What happens to those waters of hydration, did I say? They do. They just go out. They're free. They go to be with the other water molecules, which is just becomes part of your solvent, actually, then, right? So we got to kind of keep that in mind when we're working this problem. So here is my beaker. I'm going to add 8.320 grams of the hydrated salt. And what else we got? We're going to go ahead, and I should have made this a volumetric flask instead of a beaker, but assuming we can do such things, our total solution volume is going to be 250 milliliters. Now, when you're working a problem, whether you draw a picture like this or you work it not without a picture, make sure that you transfer the information correctly from the problem. How many sig figs are in this number? 4. There are 4. That's different than if I didn't have the decimal and the 0. So question mark, we're supposed to knock out, this would be for the, if you read it, says calculate concentration of the anhydrous salt. So question mark, grams of NiCl2 to liter of solution. That's my first one. We'll call that A. For the second one, I am after moles of NiCl2 per liter of solution. When I go to grade this, it's interesting how people do it different ways and we get the right answer. As long as you show all your work, you don't have to work it like I did. But I'm going to kind of do what I did before and kind of take the pieces of the nickel 2 chloride hexahydrate and kind of get at the molar masses. When in doubt, knock out a molar mass. So the molar mass of the anhydrous salt would be 1 times the decimal number for nickel, which is 58.69, plus 2 times what I call the decimal number or the weight of chlorine, plus 2 times 35.45. So you're looking at 129.59 grams per mole for the anhydrous salt. Of course, you guys are pretty good with this water now, I'm sure. To get the molar mass of water, it's 2 times 1.008, plus 1 times 16.00 gives you 18.02 grams per mole. And I'm going to do a shortcut like I did before to knock out the molar mass of the hexahydrate. So I'm going to just simply take that 129.59 plus 6 times 18.02, that's my waters. And so you're looking at 137.69 grams per mole for the hydrated salt. So we have volume, which is no problem, no worries, okay? So we somehow need to get from the mass of the hydrated salt to the mass of the anhydrous salt. And there's a few ways to do that. So I'm going to actually, if it's okay with you, since I have it on my slides, I'm going to knock out molarity first. So if I knock out molarity, I can go ahead and start with the amount of hydrated salt I added. So 8.320 grams of NiCl2.6H2I. I would usually put that over 1. Okay. And then I'm going to use the molar mass of the hydrated salt, which is 1 mole of NiCl2.6H2O over 237.69 grams of NiCl2.6H2O. Just kind of referring to the previous slide. And this is one of those where I'm going to go ahead and kind of truncate the problem here. I'm going to go ahead and plug that in my calculator. How many sig figs? Yep, 4 sig figs. Oh, I guess I'm not going to do one more thing. So this third term up here, sometimes people blow it off, but I wouldn't suggest it, because if I stop after the first 2 terms, I have moles of the hydrated salt. And I need moles of the NiCl2 without the waters. So what this third term does is it simply says for every I have 1 mole of the NiCl2 for every 1 mole of the NiCl2.6H2O. All right, fine. Now, you guys told me 4 sig figs. So you're looking at 0.03500, and units at that point would be moles of NiCl2. And we're almost done. Yeah, that's why I kind of like over here, I hit myself over the head with what am I after? So how can I use that moles of this information to get to molarity? No moles? Oh, this is going to be painful. Maybe you know, you're just not saying. I can just take that moles and divide by that volume. 0.03500 moles of NiCl2 divided by, the problem said it was 250.0 milliliters solution. I can't leave it units of milliliters, I need units of liters in the denominator. So how did we do it last time?
Times 1,000 milliliters.
Yep, very good. Times 1,000 milliliters over 1 liter. Perfect. How many sig figs?
4.
I'm liking 4, yep. So I have 4 in both of these terms. So you're looking at 0.1400, and I probably would write it this way, because at this point in the problem, I'm tired of writing things out like this. So I probably write 0.1400, capital M, meaning molar, NiCl2. And do you remember I said if you're working a problem like this and you have to find the solution concentration more than one way, kind of piggyback? So I am going to piggyback on that. 0.1400 moles of the anhydrous per 1 liter of solution. So how do I get from moles per liter to grams per liter? Just using the molar mass. So I'm going to piggyback on that to knock out A. So I'm going to rewrite our molarity. 0.1400 moles of NiCl2 over 1 liter of solution. A few slides ago, we knocked out the molar mass of NiCl2. We said it was 129.59 grams per mole. So now I can use that molar mass. 129.59 grams of NiCl2 per 1 mole of NiCl2. Units of moles of NiCl2 cancel. We're left with what we were after, grams of NiCl2 per liter of solution. 4 sig figs. Dun, dun, dun. You're looking at 18.14 grams of NiCl2 per liter of solution. And I might rewrite it G/L. So 18.14 G/L NiCl2. Just because I can, and it's the same thing. So there's just one more follow-up part to this, but that will be fine. We're just going to hold that off till Friday. And on Friday, we'll continue talking about solution concentration. Okay? So we'll see you in lab tomorrow, either 11 or 12.